The name of this video is Vector Potential from Field. In fact, we are going to discuss about the vector potential A associated with a magnetostatic field B. However, instead of doing the typical procedure, that is to find B from A, for pedagogical reasons, in this first video, I want to find A from a given B. This is rather atypical, because typically, again, we attempt to find B from A, which is usually easier. However, as is pedagogical value, therefore we are doing it here. We know that because of the solenoidal property of B, B can be rewritten as the curl of a vector potential A. In a Cartesian coordinate system in particular, we can write B as the curl of A, which written in a Cartesian coordinate system gives us three components: Bx, which is equal to the curl of A along the x component, and so this is going to be the partial derivative with respect to y of az minus the partial derivative with respect to z of ay. Then we have by, which is the partial derivative with respect to z of ax minus the partial derivative with respect to x of az. And finally, bz, which is the partial derivative with respect to x of ay minus the partial derivative with respect to y of ax. In a Cartesian coordinate system, this is the curl. Suppose that we now consider an infinite straight solenoid. We have seen this structure at the end of piece 242. So the core of this infinite straight solenoid, which I remind you is a degenerate case of a toroidal solenoid with infinite radius. And in fact, the infinite straight solenoid is one of the most important structures because its self-inductance is very useful, for example, to find the coil of the antenna I've shown you at the beginning of 242. And so in this case, the core, it's an infinite core, and so this backhand here is characterized by this cross-sectional area, and this cross-sectional area is such that the square root of A is much smaller than the overall length of this solenoid. That's why the infinite straight solenoid approximation is valid. This is the length L of such a solenoid, and this is the front end cross-section right there, still with area A. In this case, we want to wind around this core a wire in this fashion, let's say. Etc. And we want to establish a steady current, let's say, in such a way that according to the right-hand rule, the magnetostatic field within the core is going to point following the longitudinal axis of this solenoid towards the right here. And so we assume that the current I flows in this direction. So therefore, in this direction, right-hand rule B, let's call it not, which is uniform, vector is going to point towards the right, parallel to the longitudinal axis of this solenoid. We can, of course, use a cylindrical coordinate system where this is the z-axis. This would be the r-axis, and which I'm not going to sketch, and bar phi was in this direction. Again, right-hand rule, so z and b naught have the same direction. so that we can rewrite B naught as an amplitude B naught times the unit vector along the z-axis uz. There are no other components. And in fact, we know that the amplitude B naught is given by mu naught small n I, which is the current. Let's in fact call it I naught, a steady current. So in this case, a small n, it's nothing but the overall number of turns of coil divided by the length, which again is the length of this solenoid, which I didn't sketch here, but it's just this length. All right, so now that we know all of that, we know that we are in the approximation of an infinite straight solenoid, so the field is uniform, does not depend on radius or anything, it's mu naught n, which is a constant, times I naught. Let's specify this B field up here in the special case of a uniform field along the z-axis. This means that here there will be no x component, no y component, and only a B naught z component. So this is associated with this field here. I'm just specifying this generic curl of A for the specific case we are considering down here. Now, by inspection, we can solve this system of equations, which in this case, luckily for us, is rather easy. So by inspection, first of all, we set AY equals 0 in this equation down here. This implies that the partial minus with respect to y of AX has to be a constant. Therefore, AX has to be minus B naught, the minus because of this minus here, and it has to depend on y, because when I derive with respect to y, I give a constant. And similarly, in this case, you can verify that AZ has to be equal to 0 to be a solution, and I let you verify this in Piazza. It's rather simple. So verify that this is true in Piazza. Another possible solution, again looking at this equation down here, which is the key equation because it's the only one where we have a non-zero B naught on the right hand side. Now we decide to set AX to 0. Therefore, clearly I need to find two solutions here, so AX and AY, so I set one and the other equal to 0 respectively, and so in this case AY is going to be plus B naught, and this time times X, because the derivative is with respect to X. And also in this case, you can verify that AZ must be equal to 0 to be a solution. Now, these are two solutions of this system. Obviously, also linear superposition of these two solutions will be a solution to this system. So by means of linear superposition, we can rewrite in this fashion that the general solution A to this problem is comprised of two components. One is minus a coefficient alpha times B naught times y. This is the x component of A. And the other component is the y component, which is plus beta B naught x. So these are the two components of this field, where alpha and beta are two constants. So alpha and beta, I'm doing linear superposition, so I will assume that alpha comma beta are in capital R. Great, so this is linear superposition. Incidentally, if you were to compute in this Cartesian coordinate system the divergence of A, which I remind you is the partial with respect to x of AX, etc. for all the other components, in this case, you will see that AX with respect to x, well, AX only depends on y, so it's 0. AY with respect to y is only a function of x, so it's 0. AZ is 0, so this is 0, which means A is solenoidal. I remind you that among the infinite set of possible vector potentials A associated with B, you can always write a mu A tilde vector equal A plus the gradient of a scalar field psi. In fact, in the end of 342, we are going to see that this is a condition which is called gauge condition and is fundamental in the theory of electromagnetism later on, and it's very general. So in this specific case, luckily enough for us, the solution by means of this linear superposition, which we found by inspection, it's already such that A is solenoidal, but as we have seen in 242, I can, among all this infinite set of vector potentials, I can always find one which is solenoidal. Luckily for us, we ended up finding exactly that this time. However, if I were to add the gradient of any scalar field psi, I would get something which not necessarily is always solenoidal for it. We just got lucky in this case. But you can always do it in such a way that it's solenoidal. All right, we'll come back to this at the end of 342. So now that we know all that, let me ask you this question. So what are the equations of a circle with the parametric equations of a circle with radius small r? Well, let's write them in this fashion as here. So we know that the UR component, RUR, of such a circle in parametric coordinate is going to be written as x, which is equal to r cosine of r phi, and y, which is equal to r sine of r phi, where r phi belongs to the region from 0 to 2 pi excluded because it's periodic. Now, if we want to compute the tangent unit vector at this, the tangent vector at each point on this circle, this will be r u bar phi. This one is going to be given by the derivatives of this object. It's going to be x dot, where dot means derivative with respect to phi. Derivative of cosine is minus r sine of bar phi. And y dot, of course, because we're trying to find the tangent, u bar phi. And so this one will be just r cosine of bar phi. Note that, interestingly enough, minus r of sine of phi is minus y, whereas r cosine of phi is x. So now if we compare this construction here, this vector, with this vector here, so we make this comparison, what do we note? We notice that they have exactly the same kind of structure. The x component is minus y with some prefactor. The y component is x with some prefactor, so minus y x. So let us choose, in particular, alpha equal beta equal 1/2. I can choose whatever I want. This is still a valid choice, so I choose them to be 1/2. Then I have exactly this kind of construction. All right, this kind of vector, which means A has to be these components are the components of a vector which is tangent at each point of a circle with radius given by the norm of a vector. And so here you do the Pythagorean theorem for alpha equal beta equal 1/2, and so clearly you end up having b naught square over 4 times y square plus b naught square over 4 times x square. Under square root, you end up having b naught square under square root is b naught divided square root of 4, which is 2, times the square root of x square plus y square. But what is x square plus y square? Is nothing but r square, and the square root is r. So this norm is the radius of the circle, and so it's b naught half times r. In addition, we know that they has to be tangent, and so if we were to sketch this vector field, so let's sketch both a Cartesian as well as a cylindrical, in this case polar coordinate system, because we are just in 2D really. So this would be the origin as well as z, which points to the outside in this fashion. And this one would be r. And so now here we take A has to be of this type. This must be my vector A, where this radius here has to be the norm of A as we computed it up here. And the direction has to be tangent here. Therefore, the tangent unit vector here, we know that is u bar phi. So we can finally rewrite the overall vector A in two different ways, either as b naught r divided by 2 times u bar phi, or equivalently as 1/2 b naught vector, which goes along the z-axis, crossed with the r vector And note that here, if we were to explicitly define this, we know that the direction of B naught is UZ, the direction of R is UR. When I cross them, I clearly get U bar phi, as expected here. So in this case, this is what we find. It's a tangent vector potential. To summarize this video, for pedagogical reasons, I wanted to show you, as we have done in 242 in the case of the scalar potential, how to obtain a vector potential given a field, in this case a uniform magnetostatic field B. In Cartesian coordinates, we consider for simplicity a straight solenoid infinite, so that the field is uniform within the solenoid, is zero outside, of course, in vacuum. So we can simply write down by inspection the solution to this problem by linear superposition. A has two components, and we linearly superimpose them, assuming that the pre-coefficients are exactly equal to 1/2. In particular, this field is solenoidal. Then we remind ourselves what are the parametric equations of a circle and of the tangent at each point of the circle, which are these. And we notice that when alpha equal beta equal 1/2, these parametric equations are basically these parametric equations. Therefore, A must be tangential, according to going as U phi, with this amplitude, which is the radius of a circle, with radius B half R. And of course, the direction is U bar phi. So in this case, the vector potential goes around in this fashion. And the key point really here was to remember the parametric equations of a circle so that we can clearly identify the direction of A. That's it.